Okay, so today what we're going to do is put all of our 8 tests that we've learned together, and the directions on the problem are just going to be decide if the series converges or diverges. It's not going to give you any hint as to what test to use. Well, here are the 8 tests that we've learned: the nth term test, the geometric series test, the p-series test, the alternating series test, the direct comparison, the limit comparison, the ratio test, and the integral test. And then I've also given you, and mine's in color, and I put a colored version on Canvas, so if you want to print it out in color. But this is our decision maker when it comes to deciding what test to use. So it says start here, and so it says, does the problem have a sigma? If it doesn't have a sigma, then it's a sequence, and so we're going to use top heavy, bottom heavy equal to decide if it converges. If it does have a sigma, then the very first question you ask yourself is it bottom heavy? If it is bottom heavy, then we've got a whole bunch of other things to explore. If it's not bottom heavy, then it's going to diverge by the nth term test. All right, so once we decide that it's bottom heavy, the next question you're going to ask yourself is it a special series? Now, the special series that I think about are alternating p-series and geometric series. So these are the 3 special that I think about, and if it's one of those, then it tells you what your test says. If it's not a special series, then we would come down here and say, is it really close to a special series? Can we get it to line up? So if it's yes, then we pick a comparison series, and can we get it to line up? Is it less than a convergent converges or more than a divergent diverges? If we can get it to line up, then we come down here for direct comparison test. If we can't get it to line up, then we use our limit comparison test. If it's not close to a special series, then we come over here and say, does it have mixed function types? Are there factorials? Are there exponentials and polynomials? If yes, then we're going to use the ratio test to decide if it converges or diverges. And if no, then we're going to use the integral test to see what the improper integral does. So that's kind of my navigation. That's what I think about first as I do these. So let's see. We've got our first one is 1 plus 3n squared plus n cubed over 4n cubed minus 5n plus 0. So today, all of them are going to have a sigma, okay? So the first question to ask ourselves is it bottom heavy? Well, if I look at this guy, I've got n cubed here, and I've got n cubed here. So this one is not bottom heavy. So if it's not bottom heavy, then we're going to say it diverges by the nth term test. So the test we're going to use is the nth term test. We don't have a comparison series. And so what we're going to do, remember, for the nth term test is we're going to do the limit as n goes to infinity of our equation, 1 plus 3n squared plus n cubed over 4n cubed minus 5n plus 2 is equal to, if I look at that, that's the ratio of the coefficients, which is 1/4. So therefore, it diverges. Okay, ratio of the nth term test says that it diverges. All right. The next one, if we look at it, 4 over n cubed, is it bottom heavy? My answer is yes. So is it a special series? So yes, that one looks like a special series, and so when we're choosing which one, it's a p-series. So when a p-series says that it converges if p is greater than 1, and it diverges if p is less than or equal to 1. So we're going to use the p-series test. We don't have a comparison series. So for this one, our power is 3, which is greater than 1. So therefore, it converges. Okay. All right, let's see what's next. We have 1 over the cube root of n to the 5th plus 5. So this one is not quite a p-series, but it's very close to a p-series, okay? So let's look and see if we can use one of our comparison series, okay? So it's really close to a special series. So we're going to pick a comparison series and see which one we're going to use. So the comparison series, so we don't know which test we're going to use yet. We're going to come over here. So we're going to say b sub n is the sum, and we're going to use just this guy right here, which would be 1 over n to the 5/3, okay? So I'm going to go ahead and write it as a exponent, as a fractional exponent instead of a radical. All right, so now we need to know what that guy does. Well, that's a p-series where p is equal to 5/3, and 5/3 is greater than 1, so therefore our comparison series converges. So now we've got to see if we can line it up. If we add 1 to the bottom, remember it is less than a convergent converges. So if we add 5 to the bottom of the denominator, to the bottom of the fraction, to the denominator, what happens to the overall number? Well, that makes it smaller. So this guy is going to be smaller than what this guy is, so that means we can get it to line up. So we're going to write 1 over the cube root of n to the 5th plus 5 is less than 1 over n to the 5/3, which remember is less than a convergent, and so less than a convergent converges. So that's what I mean to get it to line up. The one we were given is smaller than the one we're comparing it to, so we can be less than a convergent. Okay, let's look at this guy. We have 3 to the n plus 4 over 2 to the n. Now this guy is really close to a, well, okay, so let's right off the bat though, is it bottom heavy? Is 3 to the n plus 4 over 2 to the n bottom heavy? That is not bottom heavy. So we can use our nth term, we forgot to put our term test. This is the direct comparison is what we used. All right, so on this one, we can use the nth term test. We don't have a comparison series, and we can say the limit as n goes to infinity of 3 to the n plus 4 over 2 to the n is going to be infinity. It is top heavy. 3 to the n grows faster than 2 to the n. So if it is not equal to 0, then remember it diverges. Okay, so now look at this guy. We have 5n squared minus 6n plus 3 over n cubed minus 7n plus 8. If I look at the first term on top and biggest term on top and biggest term on bottom, that one is bottom heavy, so we can't use the nth term test. It is nothing like a special series, except for I could compare it to a p-series. So remember when we have this rational function type situation, we want to compare it to a p-series. So we are going to take n squared over n cubed, and we are going to reduce it down to 1 over n. So that's what I'm going to compare it to, is 1 over n. So in that case, my power is 1, which is less than or equal to 1, so therefore it diverges. Now, this is way too complicated to be able to tell if it's greater than or less than 1 over n. So instead of using direct comparison, we're going to use limit comparison. Now remember, with limit comparison, we do the limit as n goes to infinity. We put the one that we were given, which is 5n squared minus 6n plus 3 all over n cubed minus 7n plus 8, and we divide all of that by what we're comparing it to. So now we're going to flip the bottom and multiply. So what we end up with is the limit as n goes to infinity. If I distribute my n, I get 5n cubed minus 6n squared plus 3n. Then on the bottom, I get n cubed minus 7n plus 8. So now if I look at largest term on top, largest term on bottom, they're equal, and my ratio is 5. So remember that 0 is less than 5 is less than infinity. So 5 is between 0 and infinity, so then they match. So what we compared it to diverges, so this guy diverges. Okay, so on limit comparison, they match in their converge diverge. All right, for this guy, we have 2 over 7 to the n. Now, this one is bottom heavy, and it does look like a special series. It is a geometric series. So we've got to identify r, and then once we identify r, we've got to decide if the absolute value of r is less than 1, then it will converge. If the absolute value of r is greater than or equal to 1, then it will diverge. So for this one, we're going to use the geometric series. No comparison series. So absolute value of r, remember, is what's being raised to the power 2 over 7, which is less than 1, so therefore it converges. Now, remember when it converges just off to the side, it then on the geometric, we can figure out what its sum is. So remember the formula for its sum is a over 1 minus r. So our a value, we're going to plug 0 in to our function. So we would get 2 sevenths to the 0, so 1. And our r value is 2 sevenths. So our sum is going to be 1 over 1 minus 2 sevenths, which is 1 over 5 sevenths, which is 7 fifths. So we know that this series will actually converge to 7 fifths. The partial sums will all start looking like 7 fifths. All right. We've got this one. We have the series from n equals 1 to infinity of 1 plus 4 over n to the infinity. Now, I'm hoping you recognize this. This is the definition of E. So whenever you see this, we're going to use nth term test. No comparison series, and we're going to say the limit as n goes to infinity of 1 plus 4 over n to the n is equal to e to the 4th, which is not equal to 0, so it diverges. So you've just got to memorize that guy, okay? You just have to, okay? All right, on this one, we have n squared over 5 to the n. So we have mixed function types. And remember, that's what I do, or that's when I bring in the ratio test. Now, there's a whole lot of other times when you can bring in the ratio test, but this is one of the biggest ones where I bring it in. So we're going to do our limit. So remember our limit, we're looking at the limit as n goes to infinity of a sub n plus 1 over a sub n, okay? So in our case, we're going to do the limit as n goes to infinity. We're going to take what we have and add 1 everywhere there's an n. So we're going to let it be n plus 1 squared over 5 to the n plus 1 times, now we flip the original, 5 to the n over n squared. Right off the bat, you are going to circle those polynomials because you cannot reduce those. Then the 5 to the n on top gets rid of the exponent, and we're left with a 5 on bottom. So if I rewrite what I have the limit as n goes to infinity of the absolute value. On top, I have n plus 1 squared. On bottom, I have 5 times n squared. Well, those are going to be equal, so my ratio is 1/5, which is less than 1, so we say it converges. Okay, remember, ratio test over here, does it have mixed function types? If it is less than 1, it converges. If it's greater than 1, it diverges. If it's equal to 1, we go back to the beginning because we missed something somewhere along the way. Okay. Next one, we have 1 over n times natural log of n to the 4th. Now, a lot of times when we have natural log of n, we have to get into the integral test, which is what we're going to get into with this one. So I'm going to do the integral test. It means I'm not comparing it to anything. And just like before, I think that needs to be a 2, n equals 2, or else it's a bad integral. So we're going to put that n equals 2. All right, so we're going to say f of x is equal to 1 over x times natural log of x to the 4th, and is continuous, positive, and decreasing. Okay, that's the conditions of the integral test. So I'm going to write it as a limit first. So we're going to have the limit as a goes to infinity of the integral from 2 to a of 1 over x times natural log of x to the fourth dx. Now, this is a u substitution, so u is natural log of x, so du is 1 over x dx. So if x is equal to 2, then u is equal to natural log of 2, and if x is equal to a, then u is equal to natural log of a. So we're going to write it as the limit as n goes to infinity. I'm going to run out of room on this one. So we're going to have the integral from natural log of 2 to natural log of a of 1 over u to the fourth du. Now, to save space, I'm going to write that as u to the negative fourth up there. And so I'm going to have the limit as n goes to infinity. Let's see, that would be a negative 1/3 u to the negative 3 evaluated at natural log of 2 and natural log of a. So that would be the limit as n goes to infinity. If I plug in my bounds, it would be a negative 1 over 3 times natural log of a cubed minus negative 1 over 3 times natural log of 2 cubed. And this guy, when I plug infinity in, is going to be 0. So this guy converges. So then we know our series also converges. Okay, so we're going to use the integral test there, and I had to squeeze it all in. Okay, next one, we have negative 1 to the n over n times n cubed over n to the fourth minus 3 quantity squared. So this one has my negative 1 to the n piece, so it's an alternating series. So the first thing that we need to do when we're talking about an alternating series test is we need to identify a sub n. So remember, we ignore the negative 1 to the n, and we're going to work with n cubed over n to the fourth minus 3 quantity squared. Okay, so two conditions with the alternating series test. So the first one is the limit as n goes to infinity of n cubed over n to the fourth minus 3 squared. So that would be equal to 0. It's bottom heavy, so the first condition is met. Second condition is that it is decreasing. So we're going to do n plus 1 cubed over, let's see, that's going to be n plus 1 to the fourth minus 3 squared should be less than n cubed over n to the fourth minus 3 squared. And normally, if you can get it to equal 0, then the second one is just a formality. Okay, you just have to write it. All right, so both conditions are met, so we're going to say that we converge. Okay? All right, just a couple more. We've got cosine of n pi over n squared. So remember, we talked about this one. Cosine of n pi is your alternating piece. So that's really going to be negative 1 to the n. So now I've got an alternating series. So I'm going to use the alternating series test, no comparison. So a sub n, I'm going to ignore that piece, is going to be 1 over n squared. So I've got my two conditions. So I have the limit, here's my first one, as n goes to infinity of 1 over n squared is equal to 0. So first condition met. My second condition is the decreasing. So 1 over n plus 1 squared is less than 1 over n squared. So it's met. So therefore, we converge. Okay. All right, now we have cosine of n over n squared. So this one is different. This one is not alternating because we do not have a pi there. So we're going to use a comparison test. This is very close to a number over n squared. In fact, what's the biggest that cosine can get? Well, remember, cosine is going to go between -1 and 1. So we're going to use a comparison test, and we're going to compare it to the sum of 1 over n squared, okay? Because cosine's biggest number is 1. So we know that p is equal to 2, which is greater than 1. So therefore, we converge. Our 1 over n squared converges. Now, if we're comparing the two, we have cosine of n over n squared, and we have 1 over n squared. And I know that this is going to be less than or equal to. So if it's less than or equal to, then we are at a less than a convergent. And so we know we converge. And that one, we used the direct comparison test. Okay. All right, now I have 1 over n squared minus 1. So again, really close to p series 1 over n squared. So let's try comparing it to 1 over n squared. So we have the sum of 1 over n squared. So our p value is equal to 2, which is greater than 1. So therefore, we converge. Okay, so now let's see which comparison test we're going to use. We need to be smaller than 1 over n squared because we have a convergent series, and remember, it's less than a convergent. Well, if I subtract 1 from the denominator, that actually makes the function bigger, the fraction bigger. So we are not lined up. So if we can't line up, then we're going to switch gears and go to limit comparison and do the limit of the ratio. So we're going to do the limit as n goes to infinity. We're going to take the 1 we were given, which is 1 over n squared minus 1, divided by the 1 we're comparing it to, 1 over n squared. So I'm going to flip and multiply. So that gives me the limit as n goes to infinity of n squared over n squared minus 1, which would be 1. And then 1 is between 0 and infinity. So the two series match, so this guy converges. So your question you always ask me is, what if you can't get it to line up? What if you're more than a convergent? Well, then you flip to limit comparison, okay? All right, last one, we've got that -1 to the n, so this one is also an alternating series. So we're going to use the alternating series test. So we don't need a comparison test. So again, we're going to ignore the -1 to the n when we write our formula, and so it's going to be just 1 over natural log of n. So on this one, we've got two conditions. So our first one is the limit as n goes to infinity of 1 over natural log of n. It is equal to 0. It is bottom heavy, so that one's conditions met. Second condition, 1 over natural log of n plus 1 is less than 1 over natural log of n. Natural log gets bigger, so if we're adding 1 onto our natural log, then our number is going to be bigger, so the fraction will be smaller. All right, both conditions are met, so we converge. Okay, so I think that is it for that lesson. It takes practice, guys. That's all I can tell you, is it takes practice, and it takes learning what your tests say, and it takes learning the process of of the mental checklist, right? So if it has a sigma, then the first thing we do is we check, is it bottom heavy? If it's bottom heavy, then I think about throwing it off to the side. If it's not bottom heavy, then I think about throwing it off to the side. It's out of the pack and it diverges by the nth term test. If it is bottom heavy, the next thing I think about is it one of the special series? And the special series are alternating p series or geometric. If it's not exactly one of the special series, then I ask myself, is it really close to a special series where I can use a comparison test? If it's not really close to a special series, then I come over here and ask myself, does it have mixed function types? If it does, then I can use the ratio test. If it doesn't, then I'm going to try the integral test and see where to go from there. Okay? All right, so that is all. If you have any questions, come see me, guys. Bye-bye.